All right, let's start up 4.2, writing and classifying chemical reactions. All right, so here's the concept that we're looking at here. We want to write a chemical reaction, and to do so we use an equation to symbolize what's going on in a particular reaction. So here's some rules that we can follow for writing chemical equations. The first thing that you want to do is separate the reactants from the products in the statement, or in the identification or the example of the reaction. And then next you want to write out each chemical formula. So we've talked a lot about nomenclature and going from the name of a particular chemical to the formula. So you want to do that. And while you do that, you want to identify something new, something called the diatomics. The diatomics are 7 different elements that will always be combined with another identical atom if they're not combined with anything else. So for instance, you will never write just a single N in a chemical equation. You will always write at least N2, because N never hangs out by itself. Okay, the same thing is true for oxygen, hydrogen, and all of the halogens. So that's chlorine, fluorine, iodine, and bromine. And just to give you an idea as to why these things do this, because I think that probably helps you understand this concept. If you look at hydrogen, it only has a single valence electron. And if you had a big jar of hydrogen, well, you'd have a lot of hydrogen atoms, each with a single valence electron. And it makes sense that the two of these would get together and form a chemical bond, because in that case, then they're both sharing 2 electrons, which gets them to that stability state. The same type of concept holds true for like the halogens. If you've got, let's take fluorine for example, and both fluorine atoms have 8 valence electrons, or 7 valence electrons, sorry. So there's 7 on both. So they both want the same thing. They both want an extra electron. So they're going to share, forming that bond between the two of them. So all of these 7 kind of do that same particular principle. They share electrons between themselves in order to be stable. So we'll see an example of that on the first writing example on the next slide. So again, step 1 is going to be to separate the reactants from the products. Step 2 is to write out each chemical formula. And then step 3 is to balance the equation itself. All right, so let's go ahead and do an example of one writing chemical equations. So here's the particular reaction. If potassium chlorate is strongly heated, it decomposes to yield oxygen gas and potassium chloride. All right, so the first thing that I want to do is be able to separate out the reactants from the products. So I'm going to put a purple box around the reactants, and I'm going to put a red box around the products. There you go. And the reason that I know that the stuff in the red are the products is because of this phrase right here, to yield, that guy. So to yield means to give or to produce. And you'll see that phrase quite a bit. Usually that means that the things after that phrase are going to be products. So they're going to be written on the right side of the yield arrow. Okay, so to continue then, let's go ahead and write the reaction. So first of all, potassium chlorate, that's going to be this formula. Okay, it might take you a little longer to write the formulas than me, but you get used to them. And then to yield, so the yield sign comes in. Oxygen gas, I'm going to go ahead and do that in red. Now, oxygen is one of those diatomic 7. So I would never just write O, just like I have here. It's going to be O2. Okay, O2. And then finally, potassium chloride at the end. So that's potassium chloride. So we've separated out the reactants from the products. We have written the chemical reaction. And now your last step is to go ahead and balance the chemical reaction. So potassiums and chlorines are fine on both sides right now, but oxygens aren't. So in order to balance everything out, we're going to need some coefficients. Make sure that we obey the law of conservation of matter. Oops, let's go back here. Put a 2 in front. And there you go. Now you've got a balanced chemical equation. So I have a lot of practice with this in class tomorrow. All right. So let's go over identifying chemical reactions then. So not only will we have to write the full chemical reaction, but we'll also have to identify the type of chemical reaction we see. And there's going to be 4 different types. We'll have a double replacement, a synthesis, a decomposition, and a combustion. So I want to go over an example for each one of these types of reactions. So first of all, a double replacement. Now a double replacement reaction occurs when 2 ionic compounds switch ions. So let's go over a simple one. Let's do silver nitrate. Silver nitrate, so if you wrote that compound, it would be AgNO3. And let's go ahead and add that to sodium chloride. Okay, NaCl. Now, one thing I want to mention here is when this reaction would occur, both of these materials would be dissolved in water. If you just added the solids together, they probably wouldn't do very much. So what we do is we dissolve the silver nitrate and the sodium chloride into some distilled water, and that allows their ions to interact more. We'll talk more about that concept when we get to solution chemistry. That's going to be second semester. Now, what happens is the ions switch. So if you think about what the ions are, the positive ions, better known as the cations, in this example are sodium and silver. So they're going to switch partners. So we're going to have the sodium pairing up with the nitrate, and we're going to have the silver pairing up with the chlorine. Okay, so sodium, NaNO3. I'm going to run out of room, so I'm going to go down here. And then finally, AgCl. So I guess it's pretty obvious why it's called a double replacement, because we are replacing 2 ions so that they pair up with a different anion. All right, so that's a double replacement reaction. And it's actually balanced the way that it's currently written. We don't have to change anything there. That looks pretty good. All right, let's go to the next one, combustion. It's defined as the reaction of oxygen gas with any other material to create energy. All right, so we're going to go ahead and combust ethanol. This is what my physical science class is doing right now. So ethanol has the equation of 2 carbon atoms, we got 6 hydrogens, and a single oxygen, and we're going to add that to oxygen gas. Okay, and then that is going to yield carbon dioxide plus water. Okay, and this is an example of a combustion reaction. So essentially we got another material, which is the ethanol right here, being added to oxygen. And usually anytime you've got a hydrocarbon, which is something that has hydrogen and carbon as the other material, the 2 products that you're going to create are carbon dioxide and water. So the key here is to look for oxygen gas as being one of the reactants. And if you do see oxygen gas as being one of the reactants, then you can probably bet that you're looking at a combustion reaction. Now let's go ahead and try to balance this real quick. I think it's kind of tricky. You've got 2 carbons, so let's put a 2 there. You've got, let's see, 6 total hydrogens, so you're going to need a 3 there. Okay, there's a 3. And then, get that a little bit better. And then if we want to count oxygens, on the right side you've got 7 oxygens. So if I put a 3 here, I'm going to actually be all set, because it's going to give me 6 plus this 1 oxygen for a total of 7. Okay, so 1, 3, 2, 3 would be the coefficients respectively for this equation. All right, the next type is a synthesis reaction, just defined as the combination of 2 molecules to make 1 large molecule. We can actually do this with hydrogen gas and oxygen gas. If we take those 2 and we add a lot of heat to it, usually symbolize that with the little triangle above the yield zero, we make water. Okay, we make H2O. This is a dual definition. We can call this a synthesis. We could also call this a combustion. Okay, we'll call it a combustion because we do have oxygen. So there's 2 ways to actually define this particular reaction. And again, we'd want to balance it, so we need a 2 out front there and a 2 out front there. All right, lastly, let's do a decomposition then. A decomposition is when 1 large molecule breaks apart. So we're going to go with baking soda, which is sodium bicarbonate, right there. And that breaks apart into really 3 substances. Sodium carbonate, water, And finally, I think the last one is carbon dioxide, CO2. All right? And again, we want to balance, so we need a 2 here. This decomposition doesn't occur by itself. You got to heat it up. So if you heat up baking soda, you're going to get carbon dioxide, water, and sodium carbonate out the other side. And that's a decomposition because we're decomposing the original compound into smaller things. All right, we'll have lots of practice with this tomorrow.